3.1 for the complex number system. Before we had kind of looked at some graphs of quadratic functions. Oops, where's my back button? Okay, and quadratic graphs. Usually we're looking at ones, my pen is going to be crazy, I think. And before we were looking for solutions where this quadratic graph would cross the x-axis, but in cases where it doesn't actually cross the x-axis, we end up with things called imaginary solutions. So and I will in this case for quadratics I will always have two imaginary solutions, or I can have two real solutions. So this one would have two imaginary solutions, this one would have two real solutions. And also there's an example of it only having one real solution, and that would be because it would be considered a multiplicity. This would have a multiplicity of 2 in order to get this graph. So where it only hits it one time, I have, oops, that's not a 1, I have one real solution. Okay, so a good example, if I had this graph right here, the equation for this graph might look like y equals x squared plus 1. Y might also be an f of x, that doesn't matter. But when I go to solve this equation, so I would replace my y with a 0, equals x squared plus 1, and then I would subtract 1. And I would have negative 1 equals x squared. But when I try to take the square root of it, I can't take the square root of negative 1. You might think negative 1 might be my square root, but negative 1 times negative 1 equals positive 1. Positive 1 times positive 1 equals positive 1. My pen stopped working again. Okay, so this is positive 1, so this equals positive 1. So I can't have a square root because I need two different numbers. So basically what happened is this kept happening so often that they actually defined something else. So the square root of negative 1, we call it I. Okay, and please write it with a scriptiness. That way I know it's an I. So it kind of looks like a backwards J. Just make it a little bit shorter than a J. Don't make it like swoop down. But still remember our rules for whenever we take a square root. When I'm actually solving one of these graphs, I will actually have x, just x, equals plus or minus I. Okay, and that's basically because we kind of want two solutions that will happen in some random places that we don't know, but they need to always come in pairs. So if I need to take the square root of a negative number, so they have a generic case which just says the square root of negative p, then I would take and I would factor this down, and I would get negative 1 and p separately. Since the square root of negative 1 is I would have I, but since I don't actually know what the square root of p is, I would leave it as the square root of p. So we write our i's in front of the square root sign so that it doesn't look like they're underneath the square root sign, and they're never underneath the square root sign. Okay, so a couple examples. If I have the square root of negative 7, you can't even hardly see the negative sign. So what I'm going to do is, since 7 doesn't actually have a square root, break it down into negative 1 times 7, and I will get I times the square root of 7. Okay, some things that actually have square roots. And if I'm actually solving equations, I'm going to do plus or minus. Most of the time, if you just see this thing, though, it's just asking you to find the positive one, and this would be the positive one. I have negative 16. The square root of 16 I can factor it down. Usually I just factor these down below, and I'm going to pull off -1 off to my side, and 16 is 4 by 4. So I have a pair of 4s. So this -1 out here means I'm going to have an I. The pair of 4s means I'm going to have a 4. So if I have a number not underneath the square root, it goes in front of the I. But if I have a number underneath the square root, I will have the I in front of that. We'll show you an example that will have both of them as well. So I will have the square root of -48 would be a problem you'd be given. I'm going to factor this down. I have -1. 48 would be 12 times 4. 12 will get me 3 and 4. Since I have a pair of 4s, I don't need to get it all the way down to my prime factorization, as long as I can actually get a pair of anything. Okay. However, if you have some 2s, you might want to go all the way down and get 2s as well. So I have a 4 that can come outside my square root sign. This -1 means I'm going to have an I. This 3 left over all by its lonesome self means that it gets to stay underneath the square root sign. And this was what my answer would look like. It would be 4I square roots of 3. And they actually write it a couple different ways. They also show it written as 4 square roots of 3 times I. I don't like this because a lot of people, they get really sloppy with their square root signs, and I do too. And we just have to really make sure that it does not go underneath that square root sign. It looks like the notation in the book uses is the i's actually always go in the back, so this one would look like square root of p I. I like writing the i's in front of the square root because you definitely don't get lazy and put it over it. Also, one more example so that we can see what it'll look like with a negative out front. If am I asked to find the negative square root of -64. So I can factor 64. I'll have a -1, an 8, and an 8. I have a pair of 8s. This negative sign out front, however, means that my answer is still going to be negative, even though I will actually have an I with it. So the -1 gives me an I, the pair of 8s gives me an 8. I rewrite it with the number out front, and I have -8 i's. Then we move into something called the complex number. So everything we've done so far are just simply imaginary numbers. Then we will have complex numbers, which will basically be a real number plus or minus an imaginary number. So everything we just worked with were the imaginary pieces. But a complex number might look in a generic form. They have a plus bi. So a would be your real piece, your imaginary piece would be your bi. So, for example, they use 3 plus 7i. I cannot write 10i. This is not at all what it is. This is as simple as it gets. So if I had to add them, here's a few examples in the book. I have 8 plus 6i plus 3 plus 2i. Okay, so these are two complex numbers that I'm adding together. So I'm going to add the real parts. The real parts would be the 8 and the 3. So I have 11, and then I add the imaginary parts, 6 plus 2. And I keep the I with it. Okay, so I have 8i. This is my answer. This is as simple as it gets. Okay, you can do subtraction in it as well. Just like we've always done, we need to do like terms. Just kind of think of that I as a variable. So I have 4 plus 5i minus 6 minus 3i. Whenever you're adding or subtracting these, not so much when you're adding, but when you're subtracting, and it tells you to do something, you need to make sure you put parentheses, because this negative sign needs to get distributed to both things in this back set of parentheses. So I will subtract my real number, so I'll have 4 minus 6, and then I will have 5i minus negative 3i. So 4 minus 6 is negative 2. 5 minus 3i, that will become a plus, and that will give me a positive 8i. So this is how that one would subtract when I do that. Okay, now we'll do some multiplication with just some pure imaginary numbers. And then we will change it into complex numbers. Oh, I can't spell multiplication. Okay. So, for example, they have the square root of negative 2 times the square root of negative 5. What you might want to do, which would make perfect sense in the real world, but we're working with imaginaries, you might want to just say negative 2 times negative 5 gives me negative 10, or gives me positive 10. But that is not what the answer is, so I'll just write a big X. It is not the square root of positive 10. So what I actually have to do is I'm going to factor everything. So I will get negative 1, 2, negative 1, and a 2. So what this is I basically have a pair, which you might think that that would work out nicely too. It doesn't. Okay, so I have I squared because I have a square root. So that basically is equal to the square root of negative 1 times the square root of negative 1. Whoops, this isn't a 2, this is a 5. Times the square root of 2 times the square root of 5. The square root of negative 1 is I, times the square root of negative 1, which is I. The square root of 2 and the square root of 5 right now, since I don't have to worry about these i's, I've already taken, or the negative 1s, I've already taken care of them with the i's. Now I can multiply that underneath the square root sign. So I'll have times the square root of 10. Anything times itself, so I times I, is that something squared? So in this case, I squared. Okay, and then we're going to go over here and we're going to kind of figure out what I squared actually equals. So I have the square root of negative 1 squared, because that's the definition of I. Okay, so then what I do is when I square something that's have the square root, I'm taking the square root of it, I'm just left with whatever that something is underneath. So I squared is equal to negative 1. So my answer is negative square roots of 10. Okay, so don't forget that negative. So I'll mark you wrong just for a bunch of sign errors for these ones. Okay, so another example real fast is I have the square root of negative 16. So this is a different example. And the square root of negative 25. Again, I really just want to say that that's a positive, but I can't do that. So I'm going to factor them down. I'll have a negative 1, a 4, and a 4, a negative 1, a 5, and a 5. So again, I have two negative 1s, so that will give me the I squared on the outside. I have a pair of 4, so times 4, and I have a pair of 5, so times 5. I squared really equals negative 1. So I will say negative 1 times 4 times 5, which equals negative 20. And that's what my answer would be for that one. Okay, I'm going to write I squared equals negative 1 up at the top, so we just remember that. And I might be asked to multiply two complex numbers. This gets a little bit tougher, but it's not bad yet. So I have 1 plus 2i times 1 plus 3i. So anytime I have parentheses next to each other, it really means multiplication. And I need to be sure that I actually multiply everything throughout everything. So I will be left with 1 times 1. So I need to actually FOIL these out. So 1 times 1 is 1. Okay, so when I tried to multiply 1 plus 2i times 1 plus 3i, I take 1 times 1 to get positive 1. Then I'll take 1 times 3i to get positive 3i. Then I will take 2i times 1 to get positive 2i. And then I'll multiply my last term, so 2 times 3 is 6. I times I is I squared. And then I will change this to a negative 1 with my I squared. And I will add these like terms. So I will have 1 plus 5i plus 6 times negative 1, which will really just change this to a minus 6. So I'll erase this. And then I combine like terms again. So I have 1 and negative 6, so I will have negative 5 plus 5i. So whenever I multiply these things, I should come out with another complex number. I will never have any other exponents of I. I should only ever see a positive I with just a, or it doesn't have to be positive, just an exponent of 1. Okay, but we'll go through and let's do one more like that. Okay, so another example would be 3 minus 7i squared, which will equal 3 minus 7i times 3 minus 7i. Don't forget to do those. So 3 times 3 is 9. 3 times negative 7 is negative 21i. Negative 7 times 3 is negative 21i. Negative 7 times negative 7 is positive 49i squared. Okay, so right here I can change my I squared to a negative 1. So that will really change this piece at the end to minus 49 because I squared equals to negative 1. So I have 9 minus 42i. Then I have 9 minus 49. And that will give me negative 40 minus 42i. Okay, again, this has a real part and an imaginary part, but I have to write the whole thing as my answer. Okay, and then let's do some figuring out what all my I exponents are. So remember that our definition, I equals the square root of negative 1. We've already figured out what I squared is, but we'll go ahead and just rewrite it. So we have the square root of negative 1 squared, so that equals negative 1. And then I would take I cubed, which will really be the square root of negative 1 cubed. But since I already know what I squared is, I cubed is really equal to I squared. My stuff is having a spasm. Times I. So let's go back and fix this. So I cubed is really the same thing as I squared times I. Okay, because my exponents add up to 3, so I don't really write the 1 ever though. Okay, so I squared we already know is negative 1. Negative 1 times I. That just gets us negative I. So I cubed equals negative I. I to the 4th equals I squared times I squared. I squared is negative 1 times negative 1 equals positive 1. So I to the 4th equals 1. Okay, so if you had to like make a nice table somewhere, like to write on the top of your paper or something, you'd have I equals the square root of negative 1. I squared equals negative 1. I cubed equals negative I. And I to the 4th equals positive 1. We can keep doing this forever. Basically, we'll have the same pattern that happens for every multiple of 4. So I to the 5th will equal I to the 4th times I. I to the 4th is 1, so I have 1 times I. So I to the 5th just equals I. I to the 6th equals I to the fourth times I squared. I really like writing everything in terms of I to the fourth because that way I know I have 1. So this is really 1 times, since I squared is negative 1, so I have 1 times negative 1. So I to the sixth equals negative 1. I to the seventh, I'm going to rewrite it as I to the fourth times I cubed. Since I cubed is negative I, so I'm going to write 1 times negative I. So my answer is just negative I. I to the eighth, I'm going to rewrite it as I to the fourth times I to the fourth. And my answer will just be 1 times 1, which is 1. Okay, so these are my basic things. So what I'm going to do is subtract off as many multiples of 4 as I can if I'm asked to find something, I to some power. So for your questions, you might be asked, like, what is I to the 37th? So what's the biggest number that I goes into that's a multiple of 4? Or what's the biggest number that 4 goes into? So I'm going to rewrite that as I to the 36 because I goes into 36. Or 4 goes into 36, I'm sorry, times I to the first, really. Okay, this will go to 1 since it's a multiple of 4. So I to the 37th is just equal to I, which will be your final answer. Okay, just a few quick examples. If I have I to the 58th, I have to find a number that 4 goes into. So when I think 50s and 4s, I actually think of 52. So because of cards, there's 52 cards in a deck. So I know that 4 goes into 52, so I can write it as to the 52nd. So I need all my exponents to add up to 58. And then I would have 4 more would get me to 56. And then 2 more would get me to 58. So these will both go to 1. And I'll be left with I squared, which is really negative 1. So my answer, I would write like I to the 58th equals negative 1. Okay. I to the 80th. Since 4 actually goes into 80, my answer will just be 1. So that's how I will simplify my i's down. Okay, we have one more thing, which is called complex conjugates. So remember, complex is like the a plus bi, which is the real plus the imaginary piece. And also, everything imaginary has a conjugate. But for example, 5 plus 7i and 5 minus 7i are complex conjugates. You might be asked to find the complex conjugate. It doesn't actually look like you're asked to find them, but you need to know that basically it's the same real and the same imaginary numbers, but the sign between them will be different. So when I do that, I'm going to actually multiply these out to show you what happens when I multiply them. So I would have, just a second. So when I multiply them out, I have 5 plus 7i times 5 minus 7i. Okay, so I'm going to multiply these out. I'm going to FOIL them. 5 times 5 is 25. 5 times negative 7 is negative 35i. Positive 7 times 5 is positive 35i. And then I have negative 7 times positive 7. That will give me negative 49i squared. Okay, these actually add up to 0, so I will cross them off. My I squared becomes negative 1, so I have 25 minus 49 times negative 1. My stuff is not working out. So then I have negative 49 times 1, so I will have 25 plus 49. And I will add those up and get 74. Really, as soon as you see a plus and a minus with the same numbers, you can pretty much skip this step. You can go right to one of these two steps. and just add them up. But make sure you square them and do that piece of it first. Okay. Another number is, and anytime I multiply two complex numbers, even two imaginary numbers, I will always get a real number. So I should never see an I squared in my answer. Okay, because this is a real answer, a real number. Okay, so for another example, I might have 8i times negative 8i. Okay, these are conjugates of each other. Okay, because the sign in front of the I piece is different. So 8 times 8 is 64 with a negative sign out front. I times I is I squared. I squared is really negative 1. So I have negative 64 times negative 1, and my answer is just 64. Okay. Some things I don't want you to get confused about complex conjugates. Make sure it's always the sign in front of the I. Okay. It's standard to write the I behind the real term, but I could also write it as 7i plus 5 and positive 7i plus 5. These are also complex conjugates, but they're not written in the right term. You probably didn't actually want to cross them out. And then I will have some things that are just not, is make sure that it's not the 5s that are changing their signs for that example. Okay, the other thing that we don't like, remember how we didn't like square roots in the denominator of a fraction? We also don't like i's in the denominator of the fraction. So if I have 2 minus 5i divided by 1 minus 6i. I really don't like this color on this, so I'm going to change my colors, but in order to get the I out of the bottom, where the complex conjugate is actually useful, is I'm going to multiply by the complex conjugate. I'm just going to write conjugate multiply by conjugate to get I out of denominator. Okay, so I have 1 plus 6i over 1 plus 6i. That's the same thing that we do with our radical signs. And we do that because if I were to actually divide this, I'm multiplying by 1. So in order to not actually change anything, I multiply by 1 in a different form. Okay, so I need to go ahead and FOIL out the top. And I will get 2. So 2, then my outer terms. So I have 2 times 6, which will give me 8i. Negative 5 times 1 will give me negative 5i. And negative 5 times positive 6 will give me negative 30i squared. And then on bottom, remember that I can just do 1 minus 6 squared, which is 36. So 1 squared was 1. And then I squared. So it would really be on the bottom 1 plus 36. So on the bottom, I will write 37 later on. Okay, I'll write 1 plus 36 right now. So on top, I have 2 plus 3i, so I have 8 and a negative 5. And then negative 30i squared will really change to a plus 30 because I squared is negative 1, so I will change that sign out front. So 2 plus 30 equals 32 plus 3i. 1 plus 36 is 37. Okay. With i's, the only thing that I change is actually how I write them. I like to actually write them out in separate fractions so that I can see the real piece. So the real piece is 32 over 37. My imaginary piece is, oops, I have 3. So you guys probably caught it, but 2 times 6 is not 8. I added. 2 times 6 is 12. So 12 plus 5 is 7i. So this will be a 7i. So then my imaginary piece will be 7 over 37 with an I at the end of my fraction. Okay, either one of these answers, so mine's not written very nicely. Whoops. Okay, so that's plus 7i. Generally, I accept both answers, but just so you know, the test will probably just have these answers and questions of answers in the back of the book. But for homework, I will have you guys be on page 239, and I will have you guys do 3 through 87 by 3s.